Welcome to this month's tip. This tip is based on the August 2003 tip entitled, Make Certain You Have Controlled Your Datum Features. We have expanded the original tip to include a more comprehensive explanation. Tip number 69. Make certain you have controlled your datum features. In most cases, datums are established from the extremities or high points of datum features through the use of a datum feature simulator for each datum feature referenced in a feature control frame. The set of datums will constrain the datum reference frame relative to the corresponding set of datum feature simulators. Orientation and location controlling tolerance zones applied to features on the part are then constrained relative to the datum reference frame by basic dimensions. Remember, basic dimensions are exact and are typically found inside a box on the drawing. Because of this, datum features often do not get checked unless there is a tolerance that applies to the datum feature. When we tolerance datum features, there will be a chain of sequential control based on the order of datum feature precedence reading from left to right in a feature control frame. Let's look at our first example. On this drawing, our primary datum feature A is this surface. The form, flatness, of datum feature A is controlled by the size tolerance of plus or minus 0.1 millimeters. Remember, because of rule number 1, size controls form. It is not necessary to add a flatness control unless there was a design requirement that the flatness be tighter than 0.2 millimeters. Next, we have our secondary datum feature B. The size and form of datum feature B are controlled by the size tolerance, but we also need to control the orientation of the feature axis of datum feature B relative to datum A. For this, we are using a perpendicularity of 0 if the feature's mating size is at the MMC size limit of diameter 36.16. Remember, when you have MMC, you get what we call a bonus tolerance. The bonus tolerance is equal to the amount the as-produced size of the feature has departed from the MMC size. In this case, if the part was produced at 36.12, the bonus would be the MMC size of 36.16 minus 36.12, giving us a bonus of 0.04 millimeters. The two planar surfaces that are datum features C are then controlled using this profile of a surface tolerance relative to the datum reference frame AB. The two planar surfaces must both be within their tolerance zone of thickness 0.2 millimeters. We should note that the tolerance zones for the two planar features are related, and in this case, both are located by the 19 millimeter basic dimension. If you are wondering why there is a 1.96 basic dimension on the drawing, it is there to locate the position tolerance zone for the diameter 19.45 millimeter hole. The profile tolerance controls the form, orientation, and location of datum feature C. On the second drawing, datum feature A is again this surface, but notice that the two opposed parallel planar surfaces are not controlled as a feature of size. The planar surface on the right is instead controlled with a profile of a surface tolerance that references datum feature A. The form, orientation, and location of this surface is controlled relative to datum A, which is a plane that is constrained by the high points on datum feature A. But what is controlling datum feature A? The answer is nothing. This approach leaves the form of datum feature A uncontrolled, so the flatness tolerance must be added. Now datum feature A must be flat within 0.08 millimeters. The tolerances applied to datum features B and C in the second drawing are the same as specified in the first drawing. Our first two examples show the most common case for controlling datum features when the primary datum feature has a form control or, if applicable, a size tolerance, which also controls the form due to rule number 1. The secondary datum feature is toleranced as needed, including a control of orientation or location with respect to the primary datum feature. And finally, the tertiary datum feature is toleranced as needed, including a control of orientation or location with respect to both the primary and secondary datum features. The configuration of the datum features on a given part will determine whether orientation or, instead, location tolerances must be applied to the secondary and tertiary datum features. There are some common cases for which the part configuration leads to a tertiary datum feature that is controlled relative to only one other datum feature. Our third example will show this. In this drawing, the primary datum feature is this cylindrical hole. This feature of size needs only a size tolerance applied, and again, per rule number 1, size and form are controlled. Datum feature B is this 60 mm width of the upper portion of the part. This is also a feature of size, with the size tolerance controlling size and form. Again, we have added a perpendicularity tolerance to control the orientation of the feature center plane relative to the primary datum feature A. As we can see by examining the configuration of the datum features, datum feature C needs a profile of a surface tolerance. This profile of a surface tolerance can be located relative to datum axis A, but there is no need to reference datum feature B in this tolerance. Datum center plane B would provide no constraint of this profile tolerance zone, so we have a case where the secondary datum feature is controlled relative to A, as expected, but the tertiary datum feature needs a control only relative to A, with no need to reference B. As we have seen in these three examples, it is important to properly apply tolerances to a set of datum features. To do this, we must examine the configuration of the datum features to determine which tolerances to apply to each. We must also determine which of the higher precedence datum features we must reference for each orientation or location tolerance. Remember, at Tec-Ease, GD&T rules. See you next tip.